what I've been doing since the beginning anyway. So let's now only think in terms of characters. Okay? We can actually do a lot, completely forgetting about the matrices. We're going to need the matrices when we're going to go for the invariant functions, because then we need to have a special frame, a specific frame, x, y, z, because this is our everyday language. But before we do that, we can just focus on the invariants. So the invariant is the chi here. This is your invariant. So we have the same kind of, we have the same writing. Huh? I mean, here we have essentially the invariant of the matrix representation of representation gamma. So this is the invariant of the matrix representation of transformation E in the representation gamma. A lot of representation in the same sentence. I apologize for that. So we actually can convert the orthogonality theorem that applies on the matrices. We can convert it into orthogonality theorem for characters. So we actually have two orthogonality theorems, or two flavors of the orthogonality theorem. I'm going to show both of them because we'll see that it translates very easily when you actually look at your character table. So this is the first orthogonality theorem that tells you that the sum over the different transformations, okay, A, B, C, D, of the number of elements in a class times the character of this class in this representation give you this equality. So we have actually this first set of equality. Let me not actually go through the equality because that's going to be super confusing. So we have this first set of equality that involve the number of elements in a given class. Okay. We have a second set of equality that, so those guys, it's actually 0 when you take two different representations. This one is 0 when you take two different transformations. So it means that if I have a table, let me, so we said we have this E, A, B, C, D, F, and we have the gamma 1, the gamma 1 prime, and the gamma 2 representations. The first, let me actually put them together. So we said that we have, remember how many 2-4 rotation? We have 3 2-4 rotation, and we have 2 3-4 rotation, okay? So what this first expression means is that if you take two different classes, so this guy and this guy, for example, of the same transformation, of the same class, two different representations, then you're going to have a certain sum that is equal to 0. So basically, the number of elements in a class times the product of the character is equal to 0. We'll see very concrete examples of that. Then we have the second orthogonality theorem that applies to same representation, different transformations. So same representation, different transformations. Okay, so we have two equalities that tell us, that gives a relationship between the characters in the row and in the columns. That's the idea. So we have relation in the row, relation in the column. And okay, that's just an element. So let's take one particular, the C6V character table. Now, well, I should probably write those formulas here. So the first formula said that if I take a given transformation, then the sum, sorry, no, it's actually the sum of the representations of the, the sum over the different classes, number of elements in the class, character gamma I, ck, gamma I prime, ck is equal to the number of transformation, the dimension of your group, times, of course, the delta function, gamma I prime, and the other theorem tells you that if you sum over all the classes, the product of the character of two different transformations must be in this case. Oh, there's an NK also. There's an NK here. H delta k prime. Okay, let's see how this translates into a concrete character table. So this is a character table of the C6V. What you see that you always have the first line with only ones. The way you can picture it is that in any possible point group, if you take a constant number, then of course this constant number is not modified by any of the transformations. Okay, so it stays itself. So at energy, we were going to derive Jaushinski area tomorrow. The Jaushinski area, the magnetic energy should fall into this representation. Okay, a magnetic field, which is an action vector, should fall into this. So actually, so the z component should fall here, and the x and y component should fall here in one representation. If you take a current is a polar vector. So in this case, the z component of the current should fall into A1, and the xy component of your current should fall into E1. That's how we're going to devise, or we're going to build up response functions. So let's focus on the character. So here only once, and here you see the numbers here is actually the dimensionality of the representation. One dimension, 2D, 2D. Okay? So those two guys are easy. So when you build a table, this is the first thing you're going to do. Oh yeah, again, you see you have 6 classes and 6 representations. So the number of representation is always equal to the number of classes. Okay? There's a demonstration, but let's forget about it. The dimensionality here, we have the ones everywhere. Now let's look at this particular column here. What you see is actually that we have this formula here. So the dimensionality, let me see, it's an Ly, right? So the character times the dimensionality, the sum over the product between the character and the dimensionality is 0. So dimension 1, 1, 1, 1, 1, 1, 1, 1. So it means that we have 1 plus 1 plus 1 plus 1, 4. 2D, 2D. We have 4 minus 2 minus 2, 0. And that's the same thing everywhere. Okay, here, 1 plus 1 minus 1 minus 1, 0. Minus 2 minus 2, 0. It's actually minus 4 minus 4 because you have 2 dimensions here. Okay? So that's the rule in the column. Now, if you take, let's see, a given line. So this rule here applies for all the lines except the first one. Now what you see here is that in the line, you are not going to take into account the dimension of the representation, but rather the order of the class, dimensionality of the class. 1, 1, 2, 2, 3, 3. Okay, so 3 equivalent transformations into one particular class. And again, we have 1 plus 1 plus 2, 4 plus 2, 6, minus 3 minus 3, 0. Okay? It's nice, huh? Very easy. And finally, yeah, okay, this is actually, I should have started this way. The sum of the dimensions, sorry, the sum of the characters, sorry, is equal to the, no, sorry, each of the character is equal to the dimension of the representation. Yeah, in this particular curve here. I should have started this way. Is there any question here? So I really encourage you, you have your cell phone or your laptop, Google character table. I will actually give you a website where you have all the character tables. I will have to, yeah, I'll do that at the end. Just Google it and train yourself and just check that, Of course, this is obvious, but it makes you more comfortable when you find yourself in front of a character table. You feel like you know it because you know that you have relations between the columns and the lines. So let's work out this one. So again, 1, 1, 1. This is fine. Dimension 1, dimension 1, dimension 2. Okay. And now we have, well, 4 elements here, sorry, that we need to determine. So I will have, let's say, yeah, A, B, C, and D. This one is E, 2C, no, it says 3C2 and 2C3. And then again, you can, so you know that you will have some minuses somewhere. So you can apply your formulas. I will just do for this one because we lost time, so I will not do the C3. I will just show you the results. Which means that the sum here of the dimensionality of the class times the character should be 0. So you should have 1 plus 3A plus 2B. And this one should be 0. Okay? Same thing here. 2 plus 3C plus 2D equals 0. And you can do the same, watch it for those two columns. This is dimension 1, dimension 1, dimension 2. So we should also have 1 plus A plus 2C equals 0. 1 plus B plus 2D equals 0. Okay? No, so this one, actually those two columns here, they are set by the system. Okay, this one is always 1 because it's a character of a scatter. So nothing is interesting, just ones everywhere. And the characters here is just the dimensionality of the representation. So those guys, they are always given in a sense. So once you do that, what you obtain is that, let me check. I don't have it. If I remember well, C is 0. Yes, C is 0, so D is minus 1. So what we have is 0, minus 1. Then if I take this guy, C is 0, so A is equal to minus 1. And B is equal to 1. Right? No, B is minus 2D. Yeah. No. It's 1, right? A, B, C, D. C is fine. Yes, it's 1. Yeah, okay. Now, it turned out that those coefficients are not necessarily real. Okay, they can be phases. And that's what I wanted to do with the C3 group, but we don't have time today. It turned out that for C3 group, you can demonstrate. I encourage you to have a look at the House book once you have bought it, because I know that you will run to a library after this lecture to buy the book. Actually, you have, so the C3 group is a rotation group, but it turned out that there is no rotation, there's no C2 axis. And in this case, actually, the C3 and the C, so the rotation and twice the rotation are not the same classes. And the reason is because when you combine them, they are not conjugate. Remember this conjugation stuff? You know, you have to find a transformation that transform that actually connect those two guys. And actually, with those 3 transformations, there is no way you can convert this one into this one. So they are actually separate. Although you could say, I mean, come on, this is just going one way, going the other way. Yes, but they are separate in this particular case. So then we have, let's say, you have gamma 1, gamma 2, gamma 3. They are all one-dimensional representations, in fact. And to solve this character table, what you find is that here you have a phase of 2i pi over 3, here 4i pi over 3, here 4i pi over 3, and here 2i pi over 3. And you can see that because you know the property of those phases, that 1 plus this plus that equals to 0. 1 plus this plus that equals to 0. So especially in groups that, I would say, trigonal groups, hexagonal groups, you often find these kind of characters. Now I would like to move a step further and probably take another 5, 10 minutes. Okay, try 5. To talk about the invariant functions. So it's actually only a matter of basis, right? So we have found that you can represent your transformations of a crystal in terms of the basis of transformations, which are your representation, right? Your representations are, you can picture it as a basis over which you're going to express all the transformations of your system. It turned out that we can also find, that you have matrices, and those matrices have eigenvectors. So you could also ask the question, well, do I actually have an eigenvector of my representation? So basically, what are the functions that are left invariant by this representation? Or by this one, or by this one. Okay, so we want to know functions. So I will skip that, because I really want to go very, very concrete. Let's take a super concrete example. It turned out, and this is really super powerful, that those eigenfunctions, they don't call it eigen, they call it invariant, but you can really picture it as eigenfunctions in my mind. They exist in any polynomial forms. Linear, cubic, quadratic, and so on and so forth. And they exist for polar vector and actual vectors. So here I'm just going to do the polar. The actual is very easy because the property of a mirror symmetry is just the opposite of that of a polar vector. So it's not very difficult to adapt. I'm taking my D3 group, favorite one. And I'm going to take XYZ and see how XYZ transform under those different transformations. So when I do that, I need to set a frame. So as I said, the matrix representation is not unique, but at this stage, I don't care. Because of course, I need to find a frame. I need to set up a frame. So I'm going to set up a frame, XYZ, and see how an XYZ vector transforms. So of course, under the identity, nothing happens. Under the rotation, so there's 3-4 rotation and 2-4 rotation, you can show, I'm not going to do it, but remember vaguely the matrices that we talked about. The A matrix was something like that. So of course the identity is that. So this is for the X and Y, and for the Z it's going to be 1. That's for the E. For the A I'm going to have -1, right? And 1, 1. No, it's actually -1, 0, 1. I just take my vector, transform it, and see what happens. And then I have rotation with much more interesting coefficients. So when I do that, I obtain all these terms here. Okay? Any questions here? Now what we want is to find a way, well, how those vectors, or combinations of vectors, behave not with respect to those transformations, but with respect to these representations. Okay? In a sense, those expressions here are happening for each of those points. Huh? Now I'm going to look at, so of course, my XYZ. You see that if I take the Z component, just look at the Z, this is the simplest one. The Z component transforms like 1 for E, 1, so 1 here, 1 for my C3 transformation, and -1 for my C2 transformation. So it should belong to the gamma 1 prime. So a function that fits, that fulfill the symmetries of the gamma 1 representation is Z. Okay. Now, if I look at X and Y, this is a little bit more complex, because you see that an XY vector, it's a two-dimensional representation, X and Y, and I will always transform an XY vector into another XY vector with a rotation, but still XY. So in this case, we say that this vector actually fits under this gamma 2 representation. Okay? So now you start picturing why we have this transformation. Now what is interesting is what happens for the quadratic part. So quadratic part, we take x, y, z, and we transform it. So again, the easiest one is a z, because you see that the z square is left invariant everywhere. So when I was saying that this line is for the scalar, it's not correct. It's for any function that is left invariant, which could be a scalar, of course, but it could also be z squared. Or, no, not x squared plus y squared, no, just d squared. So d squared falls here. So z is in gamma 1 prime, z squared is in gamma 1. And, well, actually, xy is a little bit more, I mean, the x and y squared is a little bit more complex, because you see that I end up with very complex relations. So what happens is that if I combine those transformations together, if I combine, let's say, x squared plus y squared, let's do that. X squared, y squared, they're definitely not invariant, or they do not fall under a specific representation. But if I take x squared plus y squared, you think that x squared plus y squared will remain invariant by f, or C3. Invariant by this one, by this one, by this one, by this one. So although x squared and y squared are not invariant, their sum falls under the gamma 1 representation. And I can do the same with the xy. If I take xy, then we see the xy will be transformed this way, and the x squared minus y squared will be transformed this way. So I build a vector. What it means is that if I take a vector that is xy, x squared minus y squared, I perform my transformations, and I will have another vector with, okay, different coefficient, but still the same vector, xy minus y squared, x squared minus y squared. The coefficients are different, but this is still the same basis. That's what I care about. Same basis. So basically, this one falls into the gamma 2 representation, and this one, again, gamma 2. Because you see, if I take xz and yz, so xz transforms into xz and yz, and yz transforms into yz and xz. So if I make a vector of that, the xz yz vector transforms into an xz yz vector. Is it okay? So then I have that. You see that z squared y squared minus plus x squared belongs to the A1 representation. Z belongs to A2, and those vectors belong to, oh yeah, okay, this is gamma 1, gamma 2, okay, this is gamma 1, gamma 1, gamma 1 prime, gamma 2. Okay, they are just different wording, I'm sorry. This is the more conventional way to represent things, so one dimension, two dimension. Now you see that we can actually start distributing our invariant functions over the different representation. So now, if I want to build an energy, Hamiltonian, build your Hamiltonian. It's actually quite fun. Let's build a Hamiltonian. And I think I will stop here. Let me check. Is there anything else I want to talk about? No, that's fine. Wait. It's fine. So if we build a Hamiltonian, and we want to build the Hamiltonian with, let's say, momentum and spins. Okay? So let's work on the momentum first. So momentum P is a polar vector. Okay? So my Hamiltonian is an energy, so it should be completely invariant upon all the possible symmetries of my D3 group. So it should fall under A1. So it means that what I have should be pz squared over 2m, I don't know, 2mz, for example, and px squared plus py squared over 2m parallel, for example. Okay? So this is the most general form of the Hamiltonian I can find. I do not know my masses. Huh? I just know they fit the symmetries. And if you have the courage to read the Luttinger paper, we derived the Hamiltonian for gallium arsenide. I think I also did it for silicon. He's actually doing exactly that in a much more fancy way because there's plane wave and so on. And then the little group of the K-vector, but it's the same idea. Okay. What else? Well, let's try to put some spin-orbit coupling here. So we could have x, y, and z. Okay, we have sigma x, sigma y, sigma z. Let's try to see if there is any way I can have a term that is a sigma z term. Okay, so sigma z falls under the A2 representation. Well, so basically the only way I can have a term that is fitting my D3 system is that if I have a product between Pz and sigma z. Now I'm introducing a new concept we're going to see tomorrow, is that if I have two functions belonging to A2, the character of the product of A2 will be 1, 1, minus 1 times minus 1. So product of the character. The character of the product representation is the product of the characters. So 1, 1, 1. So multiplying those two guys fall into A1. So I can have, in principle, a PZ that exists. Now let's look at the x and y. You see that now x and y, sorry, the sigma x, sigma y, that's my action vector, they fall into the E representation. So it's a two-dimensional representation. So if I want to have a one-dimensional representation, I need to multiply this guy by something that belongs also to E. Then I have two two-dimensional vectors multiplied between each other, projected on each other, then I'm going to have a one-dimensional object. So I want to have spin-orbit coupling, so P and sigma, so I can couple those guys together. Okay, now, and this will be the last thing I'm going to talk about today, just to open on the problem we're going to have tomorrow, is that what kind of combination can I have? I could have, let's go for it. Sigma x, px, plus sigma y, py. Sigma x, py, plus sigma y, px. Y. And what else? Two more. 2 by 2, 2 times 2, so I have 4 vectors. The four quantities. This one, plus minuses. Then I have all the possible combinations. Now what we should do, so we basically have E cross E, so we have the multiplication of the E representation. Yeah, it could be confusing, I'm sorry. This is my gamma 2 representation. Huh? It turned out that they have the same name. I apologize, it's not my fault. I don't know why they did that. So it turned out that we're going to find that tomorrow. We basically don't know. This guy is now a reducible representation. It's not the irregular. The irreducible is A1, A2, E. So now I need to write that in terms of A1, A2, and E. Okay? Now these guys are one dimension, so of course I should actually have, yeah. And this is what we're going to do tomorrow. We're going to find that in fact the decomposition of this reducible representation into the irreducible ones are like that. I will explain why. Those coefficients are actually, you can get them from the character table again, which means that among those four functions, one belongs to A1, one belongs to A2, and there is another one that is actually a vector. So keep that in mind, and we'll see that next time, okay? And then we'll see what kind of spin mechanism we have in this matrix. Okay? I'm done for this. Time for lunch.